There. So thank you very much for inviting me. It's a pleasure to be here. So can you all see the screen? I'm sharing it. Can you all see the pointer? Okay.
Good.
Good. So oops. Okay. So what I'm going to talk about, I want to introduce the topics. I put sort of the two more recent results or insight in the title, but let me begin with some motivation. So the topic, if you want to describe it, has to do with arithmetic of mirror symmetry. So you don't need to know all that much about mirror symmetry for this talk, but that's the motivation. So just to remind you or to state that classical mirror symmetry, as it was discovered in the 90s, sets up this correspondence between enumerative geometry, which is also known as the A model, and a variation of Hodge structure, which is also known as the B model. And so you don't need to know all that much, but you need to believe me that, or believe somebody that underlying mirror symmetry, so underlying this classical correspondence, there's actually, first of all, a physical duality of two physical theories being equivalent, coming from string theory. So that's one thing, and mathematically that there is underlying some equivalence of categories on the symplectic side, the A model, and the complex side being the B model. Okay, so and if you have that, then you are tempted to try to interpret whatever you find on one side of this correspondence on the other. Okay, so that's sort of the attitude that you have, and one thing that does arise in the B model, and that's I guess the interest for this seminar, is some arithmetic properties. They enter in various ways in the B model, okay, and I'll tell you about some of that. And so then you want to ask, so you want to ask two questions. Maybe one thing, the arithmetic properties of periods, so this is coming from variation of Hodge structure, do they have any interpretation in the A model? Meaning the symplectic side, or maybe in physics. And the other one, which is maybe even more, even better, so that would be whether mirror symmetry or other physical dualities have any bearing on arithmetic geometry. And no, of course, I'm not the only one to think about these kinds of things. And I want to, would argue that the answer should be yes somehow. And I want to, in this talk, give you sort of a status update on my take on this kind of questions. So what is the sort of name of the game? So again, classical mirror symmetry, which has this correspondence, really takes place in points of maximal unipotent monodromy. Okay, so that's well, that will be important. And then there is this, the enumerative geometry depends actually on the rational structure at a MUM point. And that's something that's usually not emphasized, I would say. And I mean, it will probably become clear why it's not emphasized, just because you don't see it when you look only under the lamppost, okay? So when you only look at examples, then that's not relevant. But if you go a little further, then that's actually forced on you. And I didn't want this, but the first case where this came up actually is by studying extensions by algebraic cycles. So that's something I call extended mirror symmetry. Again, all these terms, if you're not familiar with mirror symmetry, will not be, they will not be assumed. Okay, so it will purely be from inside that will explain this. And so that's sort of the first evidence. And then if you want to rescue open string mirror symmetry, so this kind of irrationality sort of threatens mirror symmetry in the traditional interpretation. And so you want to understand this better, okay? And so one of the things which, so the two recent results which make this kind of sharper, it's not a solution to these questions, but the interpretation of the arithmetic structures, but it makes this sharper. And so the first one is this, these Calabi-Yau differential equations with irrational MUM points. And so this is some work with Klemm and van Straten, and the student of Klemm, Boenisch, Kilian Boenisch. And the other, that's a theorem that was proven by my student Felipe Mueller, recently, and that is just the statement that rational two functions are abelian. Okay, so I need to explain, I guess, why these two. So these two last things, they're the differential equations with irrational MUMs and the rational two functions. That sort of is going to be, or that I view this as sharpening these questions around arithmetic interpretation of periods. But I want to, mirror symmetry. That there should be an interpretation in mirror symmetry of these arithmetic properties of periods. So my talk will actually be completely the other direction. So I will actually start with two functions. I will talk mostly about, or for a long time, about two functions. I haven't given this talk online before, so I don't know how long it will take. I might end up only being about two functions, but we'll see how this goes. Okay, so I will start with the two functions, and then I will sort of go back, talk about MUMs, and then these Calabi-Yau differential equations will appear, and then relegate all speculations to the end, okay, and try to keep it short. So I want to start just with two functions, so you don't need to know anything if you want to know what two functions are. So here's two functions. So the definition of a two function is actually something very simple. Actually, so two could also be s. Okay, so two could be any integer in this, any positive integer in this definition, but we initially call them two functions. So two functions are sort of the first non-trivial case, as you'll see, and also they have some special properties, and if you understand them, then okay, they may be the most interesting ones for some reason. Okay, so an S function, so S just a positive integer, is just a formal power series in one variable with rational coefficients to begin with, that actually can be written as a linear combination of polylogarithms. Okay, so in this fashion, so W is called this S function, and it's the sum of integers times LIS of z to the d. So you put, you raise z to this d power, so this is the polylogarithm, okay, there. So that's just the definition, but U is a formal power series, so I don't assume any convergence at this point.
Sorry, so it's sum over D?
Oh, sorry, yes, it's sum over D, yes. This is yes, okay. Right, so for those who do know mirror symmetry, so here's, of course, you will recognize this motivating example. So if you look at genus 0 prepotential, and expand it around the MUM point in the special coordinates, then you precisely get such a three function in sort of the non-singular part of this prepotential. Here the sum is over D. Right, so in this expansion, these A's in this interpretation, mirror symmetry interpretation, these ADs are rational numbers, which are Gromov-Witten invariants, and the ND, the integers that you get when you expand in this trilogarithm integers, and there are BPS invariants. Okay, so that's the motivating example. So, but let me go back to two functions. So I want to just make some elementary observations. I have this logarithmic derivative, and then you see very simply that if you have an S function, then its derivative delta W is an S minus 1 function. That just follows from the fact that the logarithmic derivative of the LIS is LIS minus 1. And then you have this shift operator. Okay, so I'm not sure what the canonical notation for the shift operator is. So the informal power series, that's something that appears. So that's also kind of obvious. You shift it, and then it still is an S function. And then you have this space of all S functions. Okay, subspace of power series. So yeah, I didn't mention this, but I assume no constant term in this power series. You can also add a constant term if you want, but it's a little bit, for example, if you want to take this delta and you want to make this invertible integration, then it's better not to have a constant term, otherwise you get logarithms. But in the mirror symmetry applications, that actually is higher. Anyway, so this is then a module over this ring where you adjoin all these shifts, and then what you can easily see. So these just basic things, but I want to ask a question, and I have to get these elementary definitions so that it's clear what I'm talking about. So if I introduce the topology on these formal power series, then actually this is rank 1, and the polylogarithm is a basis. Okay, so that's sort of, I mean, that's just the definition. That basically just the definition, right? Yeah, another, of course, trivial observation is for s equals 1, it's just a logarithm. And this logarithm actually motivates, just from this point of view, that you should look at the exponential of this thing, and then I make these definitions. I want to call, basically any statement I make refers sort of to this derivative, to the, right, so if you have an s function, I take s minus 1 derivatives, I get a 1 function, so then I can take the exponential, and then I can ask whether whether you get a rational function. Okay, so I want to call the w rational if this exponential of this thing, or that's equivalent if you take s derivatives, that's a rational function, or algebraic if you want. Then of course I want to call locally analytic if it has a finite radius of convergence in the complex topology, analytic if you can continue it to then subset of C. Okay, so that's sort of
sorry,
yes.
Johannes, when you say rank 1, you mean rank 1 as a module over this ring Z epsilon
Yes.
1, 2? I didn't quite understand this statement. What do you mean by in Z-adic topology or formal power series?
Well, that just means that, you know, Z is small. That the opens are just Z to the power times the ring, right?
Right, but how does that relate to this rank 1 statement?
Well, that's just that if you take a finite, it just converges, right? You take.
Oh,
so
I see. But
you
are
go
you
back
saying
to
that it's free of rank 1?
I think so.
I see.
Yeah, I mean, it's just this definition. If you take a finite combination, then the tail is just some power z, because this Li z to the d just starts with z to the d, right?
Wow, okay, I see. Okay, I think I see. All right, thanks.
Thank you. Okay, so it's important because it's this notion of a basis of two functions that I kind of want to make clear what I mean by that. Okay, so now let's reformulate a little bit this, so you can reformulate it as congruences among these coefficients. So, you know, if you have these two different ways of expanding this function, formal power series, and you can invert this using Möbius inversion, and then you see that that's actually equivalent to a congruence like this. Okay, so the dth coefficient and the pdth coefficient, you divide 1 by p to the s, and then you get something which is integral at p. So that's equivalent to all the nd being integer. Okay, that's not hard to see. But if you then want to rewrite this in terms of the generating function, you have the Frobenius, and you can rewrite it in this fashion. So 1 over p to the s Frobenius w sub p. So that just means you look at it at p. Okay, at this point this doesn't mean much, and that's then an integral power series with zp coefficients. So that's the equivalent definition. And so yeah, so to sort of tease you maybe a little bit, or relate to something that you know, maybe this looks familiar, okay, to some people, is related to the Dwork integrality lemma. Okay, so there's this, I don't know, I guess invented by Dwork, but features in this I think something called formal groups. In particular, appears there all the time, and it's a kind of a trivial lemma if you think about it, but nevertheless. So it relates to our w's, because you take this exponential of the one function. Okay, so you call this y, and the Dwork integrality lemma is actually just the first of these statements. Okay, so that you have a power series with a 1 as constant coefficient, and then it's equivalent to this condition for all p. This thing that the first, you know, that the tail is divisible by p. And actually, the point is that, you know, these two functions, a generalization of this, because this equivalent to the log of y, which is the w, as I just said, is a one function. Okay, so that's if you want to maybe where this can be put in some, related to something that actually has been studied before, and is actually some topic. Yeah, so something which, okay, now let me see how I'm doing on time. I don't know how interesting you guys find this kind of discussion, but I think at this point it's just very elementary. And I want to tell you a little bit more about this because, you know, I kind of find them interesting. So here's something. I don't think this is quite how it appears in the literature on formal groups. I think there you multiply these guys, but you can also invert them. So you can also you can use them to define automorphisms of this ring of formal power series. So you just multiply by something like this, okay? So by y, and then you can invert it, and that's just something you can do. But the framing, the kind of curious framing operation is the following statement: that if y, okay, so right, so you take the log of y, and then that's one function. But if you integrate it once, then that could be a two function, right? So any two function, you take a derivative, gives you one function, but not the other way around, okay? So, but if it does, then the interesting thing is that if you invert this, so this is the compositional inverse, so then the inverse also integrates to a two function, okay? So that's the interesting statement, that's something that's known as framing, okay? And that is, as far as I know, is the proof is, I would say, fairly elementary, okay? But you have to let some careful estimates, okay? So you use Lagrangian inversion and you have some estimates. There's one you have to put a minus sign here, so there's also works at p equal 2. Anyway, so this is this statement of two function. So that kind of explains why 2 is special, because it doesn't really work when you, so if you can integrate it more than once, then you frame it doesn't work, okay? You can extend this to an action of the integers, you can go to multivariables, and we'll not tell more about this, okay? I want to, well, let's say maybe a little more on this. So that's actually also a theorem by Felipe. So I just said that it doesn't work for s greater than 2, except when s is 3 and w is rational. Okay, so that's this concept of a rational 3 function. Then all the framings, actually also 3 functions. The framings are not necessarily rational. In fact, usually they won't, but there's still 3 functions. So 2 and 3 are kind of special. When it comes to this framing, gives you one reason for being interested in this. And yeah, and then there's this sort of, again, trying to connect this to something more classical. So there are some congruences, or supercongruences as they're known. So there's something called Walcher theorem, which is this statement, and then some congruences on binomial coefficients. And so that's actually equivalent to the integrality of this trilogarithm, okay? But of course, the interest here is that you prove it in general related to this framing, okay? So, right, and so now here, this is the hint to this, what's coming later. So one reason why this Li2 is special is that actually it's kind of a period or Abel-Jacobi map on this curve, okay? So it's an integral over one form on this curve, and that kind of makes it special, and this frame dilogarithm is just a different choice of coordinate on this curve. So I don't know, for some people, I don't know how many people from physics, but it's the mirror curve to the C3 or something. Okay. Right, so now we can generalize. So there we want to go to algebraic coefficients. So
excuse, extremely naive question. Are higher logarithms also given as periods, or at least as iterated integrals?
Yeah, sure. I mean, you can integrate them again, right?
Right, okay, so they're defined recursively. That's
yes.
by okay. That also, they satisfy some differential equation for
Yes, absolutely. I mean, that's satisfy a very simple differential equation. That's just the
order
derivative.
1, basically. I mean, they're by definition just integrals, so.
So the differential equation is just, the derivative is 1 of 1 minus c.
Right.
And indeed, I'm not sure exactly why I'm writing this down here, that it's just a period, but I think that makes it special, and it sort of relates okay, well, I don't know whether there are other special things about 4 and higher functions. I haven't seen so many of those, but 2 and 3 are kind of really special. Anyway, so now I want to take some number field and I want to localize the integers at a rational prime. So this is something slightly non-standard that I'm doing here, but it's very convenient. So I take the localization at P is a product of the fields, of all the local fields, of all the primes that lie above P, okay? And the reason is just that it's simpler for me to then think about Frobenius because it's just Newton, okay? So I'm just, it just allows me to identify Frobenius like this, and then I can add higher terms, okay? So, then I can define the notion of a 2 function or S function with coefficients in K by just using now Frobenius to be this on the coefficients and Z goes to Z to the P on Z, okay? So it's just, again, this condition that for all unramified P, you have this congruence on the W localized at P. Okay, so it's going to be over soon, I think, with this 2 function business. So if you want to ask questions now, that should be good. But now I want to ask these questions having to do with bases.
Would you
a little bit more?
Again, would you say what WP, what the subscript P means?
On the W, it just means that K is embedded in KP.
So it's the same series. Okay.
It's the same.
Okay.
Hi, David. Okay, so the elementary considerations are the same as before. And yeah, so at this point I haven't given you an example, but if you take roots of unity and you just twist the polylogarithm with this root of unity, then because Frobenius is just literally raising to the pth power there, that gives you an S function. And with coefficients in the cyclotomic field. And it's not hard to see that, the space of S functions with coefficients in K is, well, first of all, non-empty and also a free modulo over the same ring as before of rank equal to the degree of the field extension. So basically a basis is, you can write down bases of just S functions in correspondence with bases of this K over Q. Sort of what's then interesting is to ask whether there are any special bases. Okay, so just something that's like the dilogarithm or the polylogarithm. So that's sort of the question I want to know the answer to, and you'll see why. So, right. So when you have an abelian extension, then you can just get a basis sort of by using the roots of unity. And so here's an example. Galois group C mod 3. So that's just well, that's an S function. Okay, so there's no, again, this is okay. So this is giving you an S function for any S. When I ask in general, I'd be happy with the basis of 2 functions. But anyway, so that's the question, and there is a question: does there exist actually a natural basis for arbitrary number field? And so here's the so for example, you could ask, right? So these are rational. For abelian extensions, you get a basis of rational S functions. So you could ask whether something like this is possible for non-abelian extension. And the theorem, which is really great, I think, is that actually if you have a rational 2 function, then the coefficients are in an abelian extension of Q, okay? So in other words, you just can't have any rational 2 function with coefficients in a non-abelian extension. So, intuitively, I always thought intuitively it's quite easy to understand why this should be the case, because if you have a rationality, then you have some kind of regularity among these coefficients, right? You can sort of encode this in some finite number of data, and then there would be a lot of regularity among these Frobenius for different p, and that's known to not be the case. Or if that's the case, then you know that the extension is abelian. Okay, so that's the intuition behind this. But if you want to prove it, it's actually a little harder. So you have to there's sort of two steps, which are a little bit subtle, that Felipe figured out. It's quite amazing, actually. So first step is to show they're only simple poles. So that's something that's known, I think, as Minton's theorem or something. And then you have to sort of work with some subtle combination of this Teichmüller and Iwasawa logarithm to show that if it's, you know, if you have these congruences mod p squared, then you already have a root of unity, right? So yeah, so that's the theorem that abelian rational two functions are abelian, and you can, so presumably we have, you know, not proven yet, but it's, you know, reasonable to think for the same intuition that if you replace this with rational, then you still have a statement. Okay. Sorry, if you replace rational with algebraic, you still have a statement. But the question, and I want to weaken this and maybe ask, can you have an analytic basis? Is there a natural choice of analytic basis? And as was hinted at, the key idea would be to have something which is a solution of differential equations. And that's what so that's kind of what I want to turn to now. If there are no questions about these two functions.
Sorry, could you just give an example of a basis for k equals q adjoin I? And S can be 2, I'm fine with that. I just wanted an even simpler example than the one you gave on the previous page.
Oh.
So just for k equals q adjoin I, what's the natural basis of 2 polylogarithms?
Well, I is a root of unity, right?
I agree with that.
So you just take Li of Iz.
Okay, so you take Li of z and Li of Iz, and those are your two.
Exactly.
Okay,
Yeah.
Gotcha. Okay, thanks.
Okay. Right, so this is about two functions. Now I want to, for the rest of the talk, it seems I feel like I went really fast because it's, but okay, if nobody's slowing me down, then I will go to the second part of the talk, which is to explain, right? So that's sort of the geometry. I know how they arise and why you're interested in this question about bases. So, you know, let me go back to maximal unipotent monodromy and explain. So this is, you know, this shifting gears quite a bit, but to bring in Hodge theory and so on, but and it's something that's something has been told many times, but there's this field of definition that I want to try to, you know, point to, okay, this sort of existence of this arithmetic structure, and then there will be the examples of irrational MUMs. So we take, you know, family of Calabi-Yau threefolds, like the mere quintic. So sorry, this is B3, sorry. So like the quintic, the one thing I'm not assuming is that the number of boundary points is 3. Okay, so then the number of examples would be too small. So, but other than that, just like the quintic, and there's this, you know, associated the variation of a Hodge structure of weight 3 over B, which is the fibers of the, you know, third cohomology with integral coefficients. You have the Hodge filtration and the polarization. Okay, so this is what you can associate to this family of Calabi-Yau threefolds that you do for mirror symmetry. And I want to just review how this, you know, how these functions that appear in mirror symmetry arise out of this, and how you understand that they actually give you a 3 function. Okay, so you have this, so the monodromies are quasi-unipotent, and if you look at, so you, yeah, so this story has been told many times by from mere symmetry by Morrison and Deligne, and so you look at points of maximal unipotent monodromy, and then you get this the monodromy weight filtration, and it's a good idea at this point to restrict to some neighborhood of this point of maximal unipotent monodromy. That's where the formal power series will arise, or that's where they arise, and so then you have this, you know, so this weight filtration with the Hodge filtration gives you this mixed Hodge structure that is Hodge-Tate, so it has this composition series with coefficients just being z of minus s. Okay, just Tate twists of the integer. So and if you have, so that's what you have at the point of maximal unipotent monodromy, and what I guess Deligne pointed out is that these functions that appear in mirror symmetry are just the data in this composition series. Okay, so there are sort of two functions that are interesting, that are really intrinsic. Okay, so there's the first extension here. So there are three arrows, there are kind of three extensions maybe. So there is the first one, which is the canonical coordinate. Okay, so that's this extension. And that's just a function on this neighborhood here. And actually, if you make this assumption of small monodromy, sort of this equivalent to the statement that this vanishes to first order at the puncture. And so it's a good local coordinate there. And then, so the last arrow is actually the same as the first one by duality, using this polarization. And then there's only one arrow left, and that's actually the interesting, well, the canonical coordinate is of course also interesting. So this gives you the prepotential, or so the relation is that it's the exponential of the second derivative of the prepotential, or actually the first integral of the Yukawa coupling. Okay, so this C here, I apologize for the poor quality of the slides. Okay, I tried to use the LaTeX support in Keynote, and that's sort of the fonts that it uses. But I'm not very happy. Anyway, so this is the Yukawa coupling, and so the statement is that these two functions completely characterize this extension, or this variation of mixed Hodge structure at around a point of maximal unipotent monodromy. Okay, so now I want to you know, go a little bit further out on the limb and talk about the arithmetic structure. So yeah, delta is still the derivative with respect to Q. So that's, well, well, okay, so that anyway, so the point, these are just functions on this neighborhood, but now you actually make an additional assumption, and as I said, that's usually implicit, but it's not a priori necessary if you start from a complex family of varieties. It's not necessary that you have this arithmetic structure, but in practice, of course, these families are usually given with some kind of algebraic structure. So you have some kind of families that are defined over Q, and the family that you're interested in is sort of a complexification of this. And in fact, usually it's assumed, so, and it's true in, you know, 99.9% of all examples, that this MUM point is actually rational. So it's a rational point in this compactification of B. And if you then use a local rational coordinate, so it usually comes equipped with that, then you can localize the entire family to the formal neighborhood of this point of maximal unipotent monodromy, and then this localization is also defined over Q. So the localization to this formal disk around maximal unipotent monodromy is also defined over Q. Okay, so that's maybe my most difficult slide, perhaps, to explain. No, actually, it's not. The other ones are even more difficult. So for me to understand what I'm actually trying to say, but I hope it's you know, in the examples, it's clear what you mean by this. So the families are just given by equations where you have only integers, and the mum point is just usually it's at 0, and you know, if it's not at 0, then it has some rational coordinates. Okay, so if you have these assumptions.
May I ask a naive question?
Sure.
So this mum point is defined over Q, and you have an action of the Frobenius on the third étale homology in this case, étale cohomology. Yes. So is the action of the Frobenius somehow compatible with the weight filtration? The eigenspaces of the Frobenius. So the weight filtration is on. I mean, the third cohomology also has a decomposition, Hodge decomposition, and using that you can induce a filtration. Yes,
yes, I think that's compatible. So that's in fact. So it's in fact how the interplay that you use there. So everything that's actually my next point here, that everything actually makes sense over Q.
Okay, thank you.
Yeah. So but that's at a point of at the mum point, everything, almost all the data that you need to define these two functions, the canonical coordinate and the prepotential, make sense over Q. Mm-hmm. And okay, so you can understand it like you said, but for me, it's actually the simplest way to think about this is that just means you can get them from solving a differential equation, right? Because the differential equation, you get it just from the Picard-Fuchs equation. You just get it from
the monodromy of the fibers. That's the
So you don't need to know anything about the sort of topology to derive these Picard-Fuchs equation. That's just the round cohomology, and
right.
So that you just get these functions up to integration constants. Okay, so the integration constants, they know about the additional structure that you have, the integral structure, or in the p-adic case, about the Frobenius.
Cool. Okay.
Okay, but indeed, so that's by putting these things together. So you basically, because there is this Picard-Fuchs equation, that things agree, both the complex and the p-adic story agrees with the story over Q, but you have to fix these constants, and that I cannot even begin to explain how you show that that's actually the case. But I mean, Vologodsky and Kontsevich and Schwartz proved maybe some 15 years ago that these are actually, maybe there are some, you know, one or two slightly technical assumptions, but basically that these are the same thing. Okay, so that's how I understand what's going on, that the complex canonical coordinate is the same as this rational coordinate is the same as the p-adic one in wherever these things can be compared. Okay, and the same is true for the Yukawa coupling. The Yukawa coupling doesn't depend on the boundary conditions. On the integration constant. This Q depends slightly, and there is a sort of one rational constant there's one multiplicative constant that is an integration constant of the differential equation. And that's very hard to show that that's actually equal to 1. But anyway, so these things agree, and then using the Frobenius in the p-adic story, you can show. And so now this is the Frobenius that actually lifts the canonical coordinate to the pth power. You can show that the Yukawa coupling satisfies this kind of integrality, which if you remember back what this delta was and you integrate 3 times, what it tells you is that this f is the prepotential is a 3 function, okay, for except for a finite number of p's. Maybe p has to be bigger than 3, I think, for this to work.
All right, in your theorem, what are the a priori definitions of q, qq, and qp again?
So q is this extension class in the ordinary Hodge theory, and then qq is the extension class in the rational theory, which doesn't know about the integral structure.
I see. Okay.
But you have a similar, so it's a very similar thing, except you don't know about the integral structure. But you still have the Hodge filtration, and the key is the weight filtration, because it allows you to, the weight and the Hodge filtration are opposed to each other. So
okay.
It allows you to.
But okay, so they're just extension classes again between mixed Hodge structures, just over Q or over ZP instead of over Z. That's all that's happening?
Yeah, so that's certainly how Q and QP are defined, and then the real business is actually the differential equation, and that's how you. Okay, that doesn't satisfy you, but
I mean, if they're defined by extension classes, then of course.
Well, yeah, that's how I defined them exactly.
Then this theorem is tautological, isn't it? Like, of course, Q should map to Q sub Q. If one's an extension class, and there's, I assume, a mapping from an extension class of integral Hodge structures to an extension class of rational Hodge structures. I just don't understand what about these definitions makes this equality non-tautological.
Well, I don't know. You have to compare these different theories, right?
I mean, if I'm understanding, sorry, go ahead.
Okay, the way I think about this is that the differential equation, okay, gives you only determines these functions up to a rational, up to a multiplicative constant.
I think maybe what I didn't understand is this differential equation. I thought they were being defined in terms of extension classes of mixed Hodge structures. And then like the differential equation was a fun bonus that they happen to satisfy some Picard-Fuchs types differential equation. If they're defined in terms of extension classes of Hodge structures, I don't understand what the content is.
Well, I don't really know, but I can make a quick comment. I don't know what the middle thing is, Q sub Q, the thing over Q. But my impression was that Q sub P was some kind of a variation of Hodge structures in the p-adic category.
Okay.
Isn't that right, Johannes?
Yes, okay, I think thank you. Okay, so indeed, I think the QP and the Q are defined by some Hodge theory, okay?
So Q is defined in terms of complex Hodge theory with integral structures and so on.
And the Q sub Q is not defined by some Hodge theory, okay?
Okay, gotcha, thank you. Perfect.
Okay, that's really how you compare them, okay? So, yeah, sorry.
But if you define Q sub P in terms of p-adic Hodge theory, the comparison between that and the Q over C is also not so clear.
Sure, understood, thank you.
Yeah, I guess that's why it's in the middle, okay, but all right. Okay, so now comes the trying to make the point about why this is relevant or important for mirror symmetry. So there is this the rationality of this. Okay, so that's so if you start with a complex family and you know that it's actually comes from some rational some family defined over Q, then you find that these coefficients are rational, and that's if you don't have that, then there's no way you can interpret them as Gromov-Witten invariants of some mirror manifold, just because Gromov-Witten invariants count maps are rational by definition. Okay, and without this, there is no way you can interpret this. The other one is a little bit of a bonus, maybe because, well, I guess now there are enough integral theories which you can compare with and really be sure that that's also essential for everything to make sense. But the first one is really necessary, and one way to think about this is that, well, this is the the old way of subtracting multi-cover contributions from Gromov-Witten theory, including this trilogarithm. And right, so these integration constants, they can be calculated from global monodromy. I just want to, because I'm coming now to the examples, and so that's how you get these integration constants in the first place. Okay. So right, so there is the mere quintic, which well, many of you will have seen. So that's just the Picard-Fuchs operator. Theta is z by dz. I think it's not written here, but the periods. I had to write a period, so that actually the differential equation satisfied by the periods. You get this prepotential integration constant, and then you have these coefficients. So this tail here is a 3 function with rational coefficients. Okay, so there are many examples, but as I said, the question that's the point I want to make is that there's no a priori reason why these things should be defined over why there should be this rational structure. But you want to look for examples, and you don't find any. So in fact, one place to look for examples is this sort of list of Calabi-Yau differential equations, which are fourth order operators which have the MUM point and all the properties that you want for Calabi-Yau, or to be interpretable as a Picard-Fuchs of a Calabi-Yau. And well, the way they're constructed, of course, the MUM point is defined over Q, so then you shouldn't be disappointed if all these MUM points are over Q, but some of them actually also have MUM points at other values of Z. Okay, so there are usually more than one singular, well, more than 3, I guess, singular points, and some of the other ones are also MUM, but none of them actually have rational MUMs. However, if you actually go and talk to Duco, and then he will tell you that there are actually others which are not included, but would actually have these properties. So here's an example. So that's to make maybe the point of this integration constant that or the hidden assumption about this rationality here. So there was one operator which is kind of a strange operator, I guess was called. Looks like this and has all the properties except that the prepotential is actually doesn't have 3 integrality, but only if you twist the trilogarithm by this the quadratic character. Okay, so that is precisely the statement of being a 3 function with coefficients in Q with joint square root of 2. And in fact, you can discover the square root of 2 by fixing these integration constants. Okay, so the canonical coordinates actually doesn't start like Z, but you have to add the square root of 2. And then the prepotential just has the square roots of 2 in them, so the coefficients are not rational numbers, but the tail here is a 3 function with coefficients in this Q joint square root of 2. And you can calculate again the all the other constants as well.
Sorry, Johannes, this strange operator is also coming from some MUM point of a family. Is that what you said?
Yes, that's kind of. I can't give you the family, but the idea is that yes, it should also come from a point of. I mean, that's in principle these can be constructed. So I think this also belongs in this class. So you can construct more, a handful more. So there is something called the Hadamard product, which is some kind of you take 2 families of elliptic curves, over P1, and you sort of convolve them using multiplication on P1 or some compactification of that, and that's the Hadamard product, and is related to Schön's construction of Calabi-Yaus. And if you do this, well, doing this at the level of the geometry is hard, because you have to compactify in the right way. But at the level of the differential operators, that's actually relatively easy. And then you get differential operator which looks like this. Okay, so that's an operator you don't find on the list because it doesn't have a mum point that's defined over Q. But actually it has a mum point which is defined over Q at square root of 5. And so, you know, in this, the contrast, the difference to the previous example is you can't get the square root of 5 out of the equation in a simple way. And you calculate, you know, everything, and you still find that it's a 3 function with coefficients in Q at square root of 5. And if you,
a bunch of that's so now you have an L function showing up of some quadratic character.
That's correct. So the integration constants now. So I listed them because I, you know, thought some of you might be interested in these constants. So usually you just have something zeta of 3 over pi cubed.
Well, actually, can one understand why zeta of 3 is showing up here? I mean, and if one can show that it's an irrational number?
I don't think you can show from this that it's an irrational number.
I see.
I think Minhyung has a nice paper on the zeta.
Yeah, I mean, I will defer the question of why zeta of 3 appears to Minhyung, but
well, other zeta values show up at odd integers as well in higher coefficients, or this is a standalone thing?
No, this is the only thing that appears in dimension 3.
I see. Okay. And as far as examples go, how important is it that it's a family of Calabi-Yau 3 folds? Will a family of Calabi-Yau 2 folds work? So for example, a family of K3 surfaces?
It will not have the same properties, no. I mean, the you know.
I mean, I'm looking for, so what I'm wondering if there is an example where this Calabi-Yau differential equation is a modular linear differential equation of order 4. So if it can be defined on the modular curve somehow. If it's fine, it's just wondering if there is, because a standard example of K3 families on the modular curve are, for example, if you, for example, the modular curves of type x0n, they parameterize, each point parameterizes a pair of elliptic curves, which are isogenous to each other. So using this pair of elliptic curves, one can construct the Kummer K3 surface out of this. So this gives you a family of K3 surfaces over modular curves. And I don't know if the MUM property is satisfied. And second, in their cohomology, somehow you should cut out a degree 4 piece to get this 4th order Calabi-Yau thing. Why 4th order, by the way?
Hey, maybe this is a little bit off topic right now.
Sorry, yes. Sorry.
Well, I mean, it's you know, maybe if the MUM points that you have in your K3s are defined over, you know, what I'm looking for are irrational MUMs. So I would like to have more. So for example, one thing I'm complaining here is about is that you have only abelian extensions appearing. And for the reason that I said, that I want to know about the basis of these 3 functions, it would be interesting to have examples where the residue field is not an abelian field. And maybe the K3 surfaces, I think some of these order 4 operator actually can be constructed from K3 surfaces. So there are some constructions that involve K3 surfaces. Okay, so in some sense, that's really the 2 points I wanted to make, okay? I think they clarify the puzzles about these irrational, the irrationality or the question of rationality or not, right? So that they have this, you know, rational 2 function abelian, so you don't have a basis of rational 2 functions, and there exist, you know, there exist at least differential equations, And presumably you can study Calabi-Yaus associated with that have irrational MUMs, and then you can ask what is the mirror interpretation, which, well, is yet to be done. Okay, but I can end maybe with, that's, more examples. These are actually the first examples where this sort of, set of questions arose. Okay, so this is from the extended mirror symmetry. So you can extend these families by, algebraic cycles. And this gives you a mixed Hodge structure everywhere. The point, and then you can classify these extensions and study differential equations again. And the point is that the extension appears sort of more rapidly there, because even if your family of Calabi-Yaus is defined over Q, this curve might not. Or what's actually relevant is the localization again to the MUM point, and that's sort of the best I can explain how this occurs. Okay, without showing equation. So the localization of this curve is actually splits, and there is in each component there is of the splitting, the field of definition, which is an algebraic number field, and you can localize things like that. So you have some kind of extended disk, okay, which involves this number field, the extension class. So actually the extension is in the Jacobian for this, variation of Hodge structure, but there's a special property of threefolds. Just like before, there were only two functions characterizing this variation of the Hodge-Tate story at maximal unipotent monodromy. So here you also have one more function, okay, which is I guess either Griffith's infinitesimal invariant or the W, which is the superpotential. And by using similar arguments as before, you show that this superpotential is a two function with coefficients in K. And again, you can get also the constants from integrating from global monodromy. And so here now the example. So the first example is an old one. None of these examples really is recent, but I just want to show. So the first one is something with rational coefficients that has the dilogarithm, the ordinary one, and then here's one with a non-abelian residue field. I really want to show this because I don't know, I find it interesting to, give you a two function that's actually analytic. And the reason it's interesting is the following. So here's the example. Okay, so there's some complicated equations, and here's this global extension of moduli, right? So Z is the modulus on the parameter of this family, and then you have some extension here by A and B, and this extension splits, and so here you have two sort of branches, one which involves this residue field, the cube root of 5, and here there's a biquadratic extension like this. The point is you can study the differential equation, and you get this kind of animal here, and so the statement, okay, is interesting. So I told you that that rational two functions are abelian, okay? And here what you have is not quite, and I said probably this is true also for algebraic two functions that they're also abelian. But what you have here, not quite an abelian two function, not quite an algebraic two function, but you have a two function that satisfies an algebraic a linear differential equation with algebraic coefficients, right? That's what this is. So this L is this is the same, Picard-Fuchs operator for the quintic, and then you have this complicated algebraic function. It's a function, sorry, I didn't say what psi is, but psi is the same as z, basically. And it's an algebraic function of psi, what you have over here, because a and b satisfy some algebraic equation. So the statement is, out of solutions of differential equations with algebraic coefficients, you can get two functions with coefficients in an abelian number field. So that's kind of a substitute, I would say, for this algebraicity of two functions. Okay, and but you know, if you want to do better than this, you actually have to find a good basis, I would say. So you have to find the simplest way of doing this that still gives you a two function for the non-abelian case, or something else, I don't know. And you know, you can also calculate the limiting values. You get some L functions at s equal 2, and that might give you some clues. But I will not speculate today about this. I'm actually ending right on time, so that's very good. So again, the statement I just made, you can, you know, don't get algebraic two functions, presumably. For arbitrary number field, but something with solution of differential equation. You want to find the basis. That's a speculation that I've made on other occasions. So you can try to, right, so I didn't say much about the A model in this case, but I said that there is a Gromov-Witten theory, and if you have this cycle, then that's mirror to having a Gromov-Witten theory relative to this to a Lagrangian submanifold, or is supposed to be. And one speculation, it's a simple speculation, is that this K could be a trace field of a hyperbolic three-manifold. And these limiting values of the superpotential give you a hint that that's not totally off, okay, but there are other reasons having to do with these two functions, actually, that make you think that that's perhaps too naive. Anyway, and then I told you about these irrational MUMs, and they're even more difficult because, well, they might be more dangerous for mere symmetry because these open Gromov-Witten invariants, you know, they're much more complicated and not always defined. So you can hide a lot there in the ignorance, but not for ordinary Gromov-Witten invariants. And yeah, maybe just as a final speculation, okay, coming back to the very beginning, right? So you want to know, so what does this mirror symmetry tell you about arithmetic? So my impression, or one way to say this, right? So if you, I don't know if this is it's maybe a question for discussion, but one could, right? So certainly in physics, you don't care what the field of definition is of your manifolds, right? You just want to, I don't know, compactify string theorem. But well, I mean, you have integers which are instanton numbers, which are these Gromov-Witten invariants, and so you can, there is a sense in which somehow these Gromov-Witten invariants, if you have a mirror, then these Gromov-Witten invariants kind of, you know, select for you at least some kind of rational structure on the mirror manifold. So yeah, that's, I don't know if this makes, you know, total sense, but just some question that we, you know, maybe others have comments about this. Anyway, so I'm done with what I want to say. So thank you very much.
Thank you. Right, so regarding questions, as usual, what we'll do is start questions and then just naturally progress into discussions. I have to run myself pretty soon, but I'm leaving the session open so anybody can discuss if they'd like. Maybe I could start with just one question before I run. So you were producing these extensions from cycles, right? And then the corresponding differential equation, they were saying those, the coefficients that occur in the solutions these were what you were calling the residue field, right? The residue field was the field.
Right.
So does that residue field have anything to do with the field of definition of the cycle?
It's contained in the field of definition of the cycle.
Oh, it's contained. Why is that?
Well, I would say because the I didn't well, because the local, okay, so I don't know, you can look at this complicated thing over here, right?
Right.
So when you then expand around, I don't know, psi equal to 0 or psi equals infinity, then everything is power series.
Right.
And the field of definition basically are the coefficients of these power series. But there might be, you know, the actual coefficients might be in a smaller field.
Mm.
Does that make sense? So in this example, you know, you have these coefficients appearing. So the A and the B, the coefficients are in this number field.
Right.
But I don't know, I guess here there isn't really well, it could happen that there are that only some combinations appear.
Mm.
Right? Once you expand on this side, it could happen that you get only certain, well, that, I don't know, the coefficients land in the subfield.
Uh-huh. I see. Okay. Yeah. That's fine. Yeah. Any other questions?
For the last sentence on your speculation slide, when you say an arithmetic structure on the mirror manifold, is that the family of mirror manifolds over the base?
I think so, yes.
Okay, sure, gotcha. So the much bigger question I have is, well, okay, let's start. So the strange operator, the one whose coefficients were valued in, I forget, q root 2 or q root 5, are you saying that comes from geometry, an actual family of Calabi-Yau 3s?
I think that's, yeah, that should be true.
I mean, I have no intuition for this. Are you able to see that just because the way you built this, you can do all of those, you can do each step of that geometrically? Or,
yeah, well, okay, I hope I can do it. Okay, I haven't done it, but I believe that there is a, yeah, one thinks one can do this. Okay, I haven't done it.
Is this an operator of hypergeometric type?
Oh, no.
So actually, yeah, that's how many singular points does this guy have?
Well, it has, this has 4, right?
Oh yeah, I see. Okay, great. Okay, cool. So what happened to mirror symmetry? Like I thought, you know, as a physicist, you can show that some count of curves over on one side needs to match the period expansion on the other side. And you're saying, okay, this has clearly failed here. So, you know, what happened? I thought mirror symmetry, at least classically around a mum point, was some kind of actual statement, not just here's a thing that we've computed in a bunch of examples.
Yeah, right. I agree. I don't know what happened to mirror symmetry. That's what I want to know.
Okay, great.
So that's precisely what I want to know. I mean, okay, you know, you can put it on the list of things. You know, I mean, okay, I'm not that old, okay, to remember exactly, but in the first days of mirror symmetry, I think people had, for example, these rigid Calabi-Yaus,
okay,
which couldn't have a mirror, right? But then that was sort of explained, well, either you could, you know, embed into something high dimensional, or you could just say there's no mum point, so there's no classical limit.
Sure.
And that's actually one objection you can make to these extensions that I said, because you can just say, well, the Lagrangian doesn't have a classical limit, or some other brane doesn't have a classical limit. But that's why I think that these examples are more stringent, because you just have a mum point, and yeah, you can probably construct a family of Calabi-Yaus, which you know, localizes to something which is not defined over Q.
Okay.
And you can study the derived category of this thing. And then you can mirror that derived category, for example, somehow. Or, well, that's not.
Using what? Using like a.
No, you can reconstruct, right? Sorry, you can, sorry, that's not, I didn't mean, I actually meant SYZ.
Okay,
you can reconstruct the mirror geometrically.
Okay.
Right, and then you can just say the Gromov-Witten theory of the mirror should match this Hodge theory here.
Yeah, I mean, I don't like, nobody has proven SYZ to me either, so I don't know, but okay, sure. You're saying it's plausible that there still exists an SYZ fibration, there still exists a mirror CY3 family.
Well, I mean, the SYZ is a physics argument, right? So this is just about moduli of branes.
Yeah, okay.
So unless you can still have objectness of the type, there are singularities or something. But then that would still be interesting because it would explain, that the singularities then, introduce this arithmetic structure.
I mean, now I have a silly question. What happened to SYZ for rigid CY3s? You could run A branes inside a rigid CY3, but yet he doesn't have a standard mirror. He needs to be embedded as a motive inside this larger guy.
Well.
Oh, okay, never mind.
Well, you have to degenerate. I mean, it's
yeah.
SYZ works in a degenerate limit.
Yeah, exactly. So you're at a one point, you can apply class semi-classical reasoning. Yeah, okay. So SYZ works. Okay.
Yeah, in this case, that everything works, right? It's just like the quintic, basically.
Okay, great. So this is bizarre. Fantastic.
Okay, I'm glad I convinced you that this is interesting. Okay.
No, this was, yeah, I really enjoyed this talk. Thank you so much. This was really clear. Extremely interesting, especially, I mean, yeah, all sorts of things in that.
Well, I don't know, it's tantalizing, but
but I mean, it sounds like you can actually do it. Like shortly you will say, here's an actual family of CY3s which has this crazy behavior. Someone write down a mirror for me, you hand it to Vafa or someone, he'll give you a mirror soon enough because he'll make one up out of whatever.
Yeah.
And say, okay, count stuff, like what's happening.
Exactly, yeah.
Okay, I don't want to, like, if other people have questions, I feel like Shariar might have cut him off or something, but those last L functions that were evaluated at 2, I think, is that a right of central point? Like the sort of thing in the special values conjectures that should correspond to like a higher algebraic K-theory type thing?
I think that's what you expect. I mean, that's
okay. Good.
We calculated these numerically, and then that's what we found, and then we calculated them analytically. Also, we found that again, so we can.
Okay, cool. So the central value around which the functional equation is balanced is like 1 or something in that equation, in that situation, yeah.
No, I mean, I can just, if I understand it correctly, which is probably not true, it's an L function of a Dirichlet character, of a quadratic Dirichlet character, right?
Well, that in the abelian case, yeah.
I mean, the thing that you were showing that was on the screen that said L3 and it was
this one,
a symbol.
Oh, I see.
It's a symbol, so it's an L function of a quadratic character, basically. So the special value is that L equals 1. Oh,
and this is being evaluated at 3. Okay.
Exactly. I would have not been surprised if it was 2, but since it's 3, that's even more surprising. So it probably has something deep to say if you follow Bailenson conjectures about special values, but it would have something to say about this quadratic field Q square root of -5. But why the hell is it showing up in this F? It's pretty cool, I guess.
Yeah, okay. I mean, I know that people find this interesting. I mean, I don't know. I think it, because this family is sort of it's a natural thing that arises in this limit. So
actually, even before, why are there 5s showing up everywhere?
Sorry, why are what?
5. Well, the square root of 5s. And why does the Dirichlet character of order 5 show up? So
Well,
see,
that's
in your
because,
operator, your operator, the coefficients are defined over q squared root of 5.
yeah, that's it, right? So the coefficients here are defined over square root of 5.
Right, but why? I mean, why? So where does this equation come from? It seems like it's just being pulled out of thin air.
Yeah, that's right. That's correct. At this point, it's, you know, there is a construction for it. So you take these, there are these, something called, I don't know, Apéry family of elliptic curves, okay, which are some, you know, there's 4 singular fibers, I1, I2, the 2 I1s and 2 I5s. And this thing has, I think, 2 MUMs or something like this family of elliptic curves.
Okay.
Well, I guess it's all MUM, but one of them is not, and one of, but one of them actually is not at a rational point. One of them sits at this golden ratio, square root of 5. And if you take this Hadamard product, then, well, you take a Hadamard product at the MUM. So if you take 2 MUMs, it depends which MUMs you take. So if you take the rational MUMs, you take the Hadamard product, then you get something which is a Calabi-Yau differential operator, which has only rational MUMs. But if you take a Hadamard product with the non-rational MUM of the family of elliptic curves, then you get this operator. That's how this is constructed.
So, so what is a Hadamard product? Sorry.
It's an operation for, you take, you have 2 families of elliptic curves over P1. One is parameterized by Z, the other by W.
Uh-huh.
And then you take the product at Z times W. So it's some kind of convolution.
I see. So in the end, you get a family parameterized by a single P1, or is it?
Yes, yes.
And the fibers are now what? The products of 2 elliptic curves or something more complex?
Something like this, yeah.
Okay. So, okay, I mean, I don't know, but it would be very nice to understand all of this motivically. As in, so for example, when you take these Hadamard products, what happens to the L functions of elliptic curves which are defined over Q? And especially the Picard-Fuchs, so this interplay between the monodromy of the Picard-Fuchs equation and well, which is basically capturing the vanishing cycle and the arithmetic of the MUM point. So I get, but I think it's difficult because even figuring out the field of definition of the MUM point right now is surprising, I guess, or is not completely clear. But by motivically, I mean, what is happening to L functions? So for example, if you know the monodromy, can you say something about the L function of the MUM point?
Yeah, no, I totally agree.
I mean, over an algebraic number field.
At this, I mean, I haven't, it's, there is a construction, but it's not completely easy. And in particular to get, this Hadamard product, to get something, an actual geometry has not been done, okay?
I see.
And in particular, how to, from the way I described it, it sounded like this Hadamard product was completely algebraic operation, right?
Yeah.
But certainly the zeta of 3 or this L function at 3, you don't expect that to show up in the elliptic curve. Maybe that's what you're complaining about, no? Isn't it?
Yeah. No.
Yeah, I don't know the answer to that question. I don't know the answer to that question, but that's just, we take this operator and we just calculate like we usually do, and we find those numbers.
I see. Well, that's cool. And so I have to run, but just one quick question. And this was about finding these bases for the 2 rational functions or rational
S functions, yes.
And so if you can, sorry, may I request if you can go back to the slide, and it is actually related to a question that Arnav asked about the example of Q adjoint I. And I was, well, just wondering two things. Number one, what effect does the class number of the abelian extension have? And secondly, do you actually get an action of the Galois group of this abelian extension over the space of rational two functions? So
yeah, okay. So okay, so the class number does not show up as far as I know. There's no, it's a, you know, these two function depends on very little.
mm-hmm.
Right, and for abelian extensions, it's in some sense really boring because it just twists by roots of unity.
Right.
That's why I was so, keen on pointing out that these non-abelian examples. But for non-abelian examples, it's yeah, I don't know. I find it it knows something more interesting, I think, in the non-abelian case. And the other, the Galois group, certainly in the abelian case, it's clear, but also in the other case,
the abelian case is just acting by conjugating the root of unity in L.
That's, yes. That's right,
A to Z,
it just acts on the coefficients. I mean, that's not.
Right. There's nothing there.
As you were discussing these extensions, could I ask about something even more speculative, which is what's supposed to happen at points other than the MUM point? For example, either you or not you, I forget who was studying this, you studied expansions about the conifold point of the mirror quintic, I think. And this was either your group or Albrecht's groups, and I keep messing them up because
I think it's Albrecht.
This one's Albrecht.
I try to avoid the conifold, but yeah, go ahead.
No, it was just somehow a very similar story where it seemed like they were studying period expansions about the conifold point and saying like vague arithmetic things about them. The first statement was something about an L value showing up, which is, that's fine, I think. It's about as interesting as it is here, which is, okay, it's okay. And then I don't remember because I haven't seen these talks for a year or so now, but something about expansions about that point might also have some extra arithmetic structure. And it had the same feeling as the sorts of things that you study in classical mirror symmetry about MUM points, just, okay, there are other interesting points on the moduli space, we could expand about those. And okay, certainly, for example, orbifold points, we all know you can do some kind of FJRW theory, and again, there's probably some statement. Do you expect other points in moduli space where you can expand and have some kind of analogous theory?
I can't say, no, I cannot speculate beyond what you said, or.
That's totally fair.
I mean, I think I wasn't aware actually that Albrecht was also interested in the expansion about the conifold point. I thought they were mostly interested in the actual limit.
Oh, okay. I might have made that up.
You just these L values, and then there's some modular form that appears.
Yeah, okay. But I mean, yeah, that's somehow that's fine, but I don't have anything more to say about that, I think.
And well, and then I mean, it's what is it? I think Albrecht says it's the mass of the D6 brane or something. That's
sure.
Okay. That has this, and you can, the mass of the D6 brane is some number. Okay.
Yeah.
And that happens to be an L value.
Yeah, but yeah, there's somehow nothing more to say about that. Okay, it is, and that's fine. I see. Okay, at some point I was motivated by these, the canonical coordinate, which as you noted is some kind of X class in a mixed Hodge structure. These guys also exist from Hodge theory about other interesting points on the moduli space. And you have some kind of canonical lifting of an ordinary point, mod P. And at some point I had this hope that maybe about all attractor points, we would again have canonical coordinates and we would be able to consider expansions of the Hodge structures and get some kind of point of view on the mirror. And then everything crashed down because the attractor points weren't even defined over cube R in the first place. So, okay, that was that was an ill-conceived attempt, but I don't know. That's as much as I hoped for there, just to get analogs of this kind of theory at other points as well.
Oh, so you is it something like you know in over C we know we have canonical coordinates at every point in moduli space, and you want to have something similar over?
Yeah, there were other canonical coordinates coming from p-adic Hodge theory. And
okay.
Just the same way that you had your around about the mum point, your Q matching your QP, and it seemed like some magic might happen as a consequence of that. And I don't know, I can't say more about that. I was hoping to get something analogous at other points in moduli space.
Yeah, I haven't studied these things at other points in moduli space. Yeah.
Well, no matter.
I mean, yeah, you could, something now you could do is, but you could study other orbifold points which are irrational, for example. But
sure.
It's not going to help you to solve this because, well, they don't have any good integrality.
Mm-hmm. I agree.
I mean, yeah, I cannot. I mean, there's some time ago there was this OSV conjecture,
sure,
which was supposed to give you a BPS interpretation everywhere in moduli space somehow.
Yeah, but then
there should be an integral structure everywhere in moduli space,
But okay, I don't know. I haven't kept up with it. I thought the OSV conjecture kept being wrong like over and over again.
Yeah, I mean, maybe something is still true on this along these lines, but it's much more complicated than what they thought. So
yeah, sure. Oh, yeah, okay. Good luck finding the interpretation on the mirror side. That seems.
Well, that's why focusing on this thing is. But even that, I mean, this reconstructing the mirror of these things is not so. Sure. Anyway.
Yeah, I feel like I also saw algebraic integers show up in some other context. I was trying to search, but I couldn't find it. I think maybe in one of Andy Knightsky's talks on Minahan-Imishensky theories, or one of the whole guide to more Knightsky plethora of stuff. He again had algebraic integers coming up as solutions of some actual equation, which he explained as something, but I think those were asymptotics of growths of BPS states. So, okay, that's fine, but clearly not the same thing. This seems crazy, and okay, I don't know, good luck.
Yeah, okay, look, it's, what do I know?
Okay, well,
can we speculate freely? I mean, maybe I should have written this here, but this Galois group, you asked about the Galois group, and maybe the correct answer should have been, if this is correct, then the Galois group acts on the space of BPS states.
Okay.
This is another reason to be excited. I mean, right, and so yeah. So that would be cool.
Okay. Yeah. All right. Yeah. There's still the question of what actually matches on the A side to this. Oh, I see. You'd say maybe there's some kind of Galois covariant thing on the A side, and you have to count things with.
I mean, it would be cool if you had a statement that Galois spaces of BPS states are actually Galois representations somehow.
Okay, sure. Okay, well, hold on a second. I mean, in some sense, they quote unquote obviously are. Because, what are they? They're like some kind of cohomology of a sheaf moduli space, where there's an intense amount of bells and whistles that you need to put on that, but okay, in some sense, that's true. And then if you believe that these sheaf moduli spaces are defined over Q bar, over some number field, then there is a Galois group that acts on it. Is that what you're finding here? Okay, maybe actually, probably. What can one do with that statement? Yeah, I've never thought about that. Yeah, these guys do naturally seem to carry Galois representations. I don't know if there's a natural next question, like, a natural next question could be go through Langlands and dissociate an automorphic form to that and see if that shows up physically, but I don't know if I believe that. Maybe. Well, yeah, okay. I mean, sorry. Like, clearly, I'm thinking in the old language where, you know, BPS states had integral dimensions, and this is apparently no longer a thing that's true, or I don't know how to interpret it, at least.
Well, yeah, I don't know. I don't want to be. You know, it's for the open, in the open case, I was open-minded, and you know, all things could go wrong. But now in this other case, you know, I don't know. Let's see.
Yeah, this is absurd.
It has some kind of explanation. Maybe the explanation is not that revolutionary.
Sorry. I thought there was an argument by supersymmetric localization that the coefficients in this expansion of the Gromov-Witten free energy were the dimensions of these BPS states. And you're saying, no, they're not even integers. They have root 2's in them. Okay, what the heck?
Yeah, look, I cannot give you the manifold which has this, but it's, but I might soon, you know, so.
Yeah, okay, yeah, maybe that's if I were presented with all this evidence, I would say, okay, it looks like there's probably not a manifold that realizes this. So that certainly seems like the weak link right now. And okay, if you can get that, then there's
okay. I didn't claim that I have a manifold that realizes this. I just said I have a differential equation, and then
yeah, okay.
You can, you know which one there are two sort of, I would say, two pieces of evidence, and you can be more convinced about one than the other. I don't know. We'll see.
Sure.
All right. So you were in Cambridge, or were you?
Yeah, I'm still at Cambridge at Harvard here.
Okay.
Yeah.
And what's it like? You're in your office? You're allowed to go in your office? Or?
Yeah, the office seems pretty accessible since sometime in the summer. Yeah, I don't know. It's lonelier than usual, but not dramatically different, I suppose. You're at home, I suppose, because it must be around 10 o'clock for you.
No, I actually stayed in the office. It's 10:30, but the internet at home.
Oh, I see.
Is really bad in the evening. You can guess why.
All right, that's fair.
No, really. I mean, there's sometime between 9 and, you know, well, basically 9 p.m. and 12 p.m. Just very slow. So I thought it's too risky.
That's fair. Well, it's not that long a walk for you to home. So.
No, it's just a 10-minute bike ride, and
it's doable.
All right, but I should go anyway.
Yeah, absolutely.
So, well, thank you, and
thank you for this.
Are you coming to this seminar every week? I mean, is that?
It's kind of what Min-Hyung said at the beginning. Is that at the beginning, I generally did, and then there was some sort of fatigue that set in, and it was if the topic looked interesting and if I had time. Well,
I think I came once or twice. I came to your talk, which was like the second or third talk in the series.
Yeah, I think so.
I remember that, but it's, if I'm at home and it's 9 p.m. and the kids are around.
Yeah, sure.
It's actually not that easy to go, and then the internet is slow. And okay.
Yeah, that's a very valid reason to not go.
But, I did not indulge quite as much as you did in the seminars, in the online seminar.
Sure.
All right.
Good to see you.
Take care. Bye.
See you.